Consider we have a large enclosure with the internal surface of T. The large enclosures generally act as a black body because the internal surfaces will absorb all the radiation emitted inside the enclosure. Let's say if there is a small pinhole here that there is a incident thermal radiations coming in, and this radiation, even if not at once, after a few reflections, it's going to totally get absorbed in the internal surface of that. So the large enclosure is going to act as a black body. Now, if we have a very small object inside that, this is going to be the surface area of A, and temperature, let's assume the temperature is equal to the temperature of the surface. So they are in the thermal equilibrium. Since this surface area is very small, or this body is very small, it doesn't really interfere with the black body nature of the large enclosure here. Now, assuming that this small body has the emissivity of epsilon and the absorptivity of alpha. Now, the black body is just emitting thermal radiation by EB, which is sigma T to the power of 4, the surface temperature of that. Now, part of that thermal radiation is going to get received by this small object. So we are going to have some G of absorption here, and we know that this G of absorption is going to be alpha G, the amount that is getting received for this small object, and it's going to be alpha sigma T to the power of 4. So this G is coming from the surrounding medium. So this is the radiation absorbed by the small body. And at the same time, since it is at the temperature T above the absolute zero, is emitting some energy in the form of E, and the radiation emitted by the small body is going to be a fraction of the radiation emitted by a black body by the emissivity ratio. So E is going to be epsilon EB. So assuming that if this small body was black body, and now this is the real surface, so it's going to have this fraction of that by emissivity. So it's going to be epsilon sigma T to the power of 4. Now, since the small body is in the thermal equilibrium, is in thermal equilibrium, then Q net for this small object is going to be 0, and the Q net is going to be the total energy absorbed minus the total energy that is getting emitted from that. So the total energy absorbed is going to be the surface area and the amount that is getting received, which is alpha T to the power 4, the G of absorption. This is per unit area times the area is going to be equal to the area epsilon T to sigma to the power of 4. So from here, what we can say here is the total hemispherical emissivity is equal to the, or epsilon is equal to the alpha, which is the total hemispherical absorptivity. And that's what we call Kirchhof law. And we're going to use this a lot next for analysis of the radiation heat transfer equation. So what does that tell us is the total hemispherical emissivity, which is epsilon, is equal to the total hemispherical absorptivity, which is alpha, provided we are in the isothermal condition exists for this small object, and the net heat transfer, the zero net transfer occurs in the system.